Let's run through a few calculations. It's best to think of the Poisson process as counting the number of events. In other words, nt is counting the number of events by time t. The increment, nt minus s, is looking at the number of events over the time interval s to t. And the increment has this Poisson distribution, a distribution over the natural numbers. And now we're kind of ready to look at how to evaluate some expectations. So we're making maybe some kind of a prediction. The expected value can be regarded as a prediction of something in the future, some uncertain quantity. So in kind of general, you would take some function f of, say, the increment, and now you're computing the expected value. How do you do this? Well, you take the value against the probability of that value being realized by the increment, and you sum over all possible values of the increment, which is 0, 1, 2, 3, and all the way out to infinity. Most basic type of calculation is the expected number of events in a time interval s to t, right? So the expected value of the increment. And let me just run you through how we get this. There are a few small tricks that you have to get good at, and then these calculations become fairly easy. So we set it up. This is going to be a sum of n times the probability of that increment, taking the value n. And the first thing to realize is that the very first term in this infinite series here is going to be 0. At n 0, the summand is 0. So I'm going to sum up from n equals 1 instead. The other thing you see is that there is a cancellation here. The n cancels out with the factorial, leaving n minus 1 factorial downstairs. And so now, I'm a little bit stuck. It's kind of like, what do you do with the sum? And what you want to do is try to reduce it to something that we do know how to sum. And one thing that we do know is that the probability of the increment is a distribution. And so if we sum this up over all natural numbers, so 0, 1, 2, 3, all the way out to infinity, we better get 1 because the increment has to be somewhere. Now we've exhausted all probabilities, and so we at least have this identity that the sum of this quantity here from 0 all the way out to infinity is going to be 1. And so that's the kind of thing we're after here. So what we do, if we're clever enough, we pull out the mu times t minus s term, and the reason for doing this is that now the exponent and the factorials match. And so you see that n minus 1 appears in the exponents there, and also in the factorial. And now, since the sum runs from n equals 1, we're actually doing exactly this summation above. So we're actually summing up over the distribution of the increment. The first value is 0, and that's the probability that the increment is 0, then 1, then 2, and so on. And so this whole sum down here just becomes 1, leaving the mu times t minus s. So that is the prediction for the increment, our best prediction for the increment, and it makes a lot of sense. T minus s is the length of the interval, so if we give it more time, more events are going to happen. If the rate is large, again, more events are going to happen. If the rate mu is small, less events are going to be counted from s to t. So this makes a lot of sense, and the calculation had a couple of small tricks, but easy enough. Here's a calculation for the variance. So variance has two terms, second moment and the expected value squared. So here's the split on those. The second one we already know, that's previous slide, squared. Right? We had the expectation is mu times t minus s, so I just squared it here. The second moment is going to be a little bit more tricky. First things first, we can again sum from n equals 1, because at n equals 0, that summand is 0. We're multiplying by 0 squared. That's 0. The next part here is going to be a couple things happening. So first thing I'm going to do is I'm going to take one of these n's and cancel with the n in the factorial, leaving me with an n minus 1 factorial downstairs. And also an n is left because there was an n squared here. So this n minus 1 plus 1, I'm going to need this in a second. But for now, the minus 1 and the plus 1 actually cancel each other. So it's just left over with the n. the n squared lost one of the n's to the factorial, and now there is just an n there. The other thing is we are going to again do this previous trick of pulling out the mu t minus s to get us an n minus 1 in the exponent. So we're trying to set up something that looks like the sum over the distribution again. And the reason for now subtracting and adding the 1, like I did here, is to try to match the n minus 1 everywhere. I have the n minus 1 in the exponent, I have it in the factorial, I now need it in the multiplier. Because we're, kind of at this point aiming to get not the sum over the probabilities, but maybe the sum against the values, which will allow us to use the expected value formula from the previous slide. So in other words, I have the n, and that's inconvenient. I need to match the n minus 1, so I add and subtract the 1, and that leads me to two terms. One of them involves the n minus 1, of course, and the other one has the 1 next to it. The 1 corresponding to the 1 is in fact the sum over this distribution once again. So that's simple enough. That's where this one comes from. And this second summation here is nothing other than the expected value of the increment. It's just summed a little differently. So it's still, the first value is 0 times the probability of the increment being 0. The second value is 1 times the probability that that increment is 1, and so on and so forth. And so not surprisingly, I'll get mu times t minus s there, the expected value for the increment. And now it's just about summing this up. It looks like there's a nice cancellation that happens. The 1 here keeps the mu minus s, so we keep that one, and this cancels with the second term, this guy right here. And surprisingly, we get that the variance is the same as the expected value, which is quite interesting. What it basically is implying now is that our prediction for the size of any increment is mu t minus s. The prediction came from the previous slide. That's right here. But now the uncertainty involved is the standard deviation. All right, so it's kind of like mu plus t minus s plus or minus the standard deviation, which is the square root of that interval. So you can see that there's quite a bit of uncertainty around the prediction there. But that gets you kind of the right formula and sort of the right conception of how much how much your prediction is going to be deviated. Next, let's look at the autocovariance function. We saw this for the Brownian motion, and similar tricks are going to apply here. The autocovariance is actually listed here. It is the covariance of the process with itself at some, at two different times, hence the term auto in the covariance part. And so the key kind of part of this calculation is really just this expected value of the product, because we know the expectations separately, so we don't have to worry about this term. And just like in the case of variance, we only have to look at this expected value of the product. So here there's another common trick that one uses, which is the independence of increments property of the Poisson process. This is very similar to the Brownian motion. All I'm going to do is, and by the way here s is less than t by assumption, we're going to add and subtract n at time s. And the reason for doing this is to try to get this this here increment out. And on the next line, this reduces to the increment times ns plus something that we already do know how to compute. This expected value, this second moment, is something that we already computed on the previous slide. And the reason for doing this is because ns is just ns minus n0. In other words, the Poisson process always starts at 0. These increments decouple, right? They're independent, and so their expectation of the product is just the product of the expectations right here. And in the meantime, you can see that I've replaced the second moment with the definition of in terms of variance and the expected value squared. So the variance is the second moment minus the expected value squared. Therefore, the second moment is just the variance plus the expected value squared. And so all of these items at this point we know, we've computed. Here, this first term here corresponds to the product of the expectation of the increments. This next part it constitutes the variance, and this part here is the second moment squared. No, sorry, the expected value squared, right? Okay. And here's the simplification, right? What happened here is that there's a cancellation with this s and this term right here, and that simplifies to mu squared ts plus mu s. So now all that remains to get the autocovariance is the subtraction of the two expectations. We do this by subtracting from the original result. So this is the original result for the product of the two, the expected value of the product, minus the product of the expectations. One is mu t, the other one is mu s. That gives mu squared ts. And once again, you have a nice cancellation right here, leaving you with mu s. And then, of course, this assumption is the thing that led us to that formula without any loss of generality. If we had assumed that t was less than s, you get mu t, and that gives you that the autocovariance function for the Poisson process is the rate times the minimum of the two times. And you can compare to how similar this is to the Brownian motion, where instead of mu, we would actually have the volatility squared for that calculation. So the fact that both processes are derived from a random walk is likely what's leading to this similarity. The next thing we can do is look at some conditional probabilities. The first one could be looking at the probability distribution of an increment, given that the process started in some value. And here, right away, you see that by independence of the increments, this conditioning event really doesn't really make a difference. In other words, nt minus s is this increment. It's independent of an s, which is the increment from 0 to s. And so the conditioning drops out. This is irrelevant, and we can right away make this claim. So therefore, the conditioning here didn't do any good. Here, I'm writing out a little bit of sort of how you would maybe more rigorously prove this. A lot of this comes down to properties of the conditional expectation, not the conditional probability, which is defined in terms of the conditional expectation. So really, what these probabilities above are represented by, or how you should read them, are really expected values of random variables that are indicators. So expected values of indicators of events are probabilities of those events, and then you would apply the correct property of the conditional expectation, which in this case is independence. When you're conditioning on a random variable that's independent of the one that you're taking the expected value of, that's the same thing as taking the unconditional expectation of the original random variable. So let's run through the calculation of the following. So we saw that the conditioning didn't matter for the increment because it was independent of the conditioning variable. Here we're going to look at what looks like a transition probability of sorts. It's saying at time s we're at the value k, and we're going to look at the probability of being at state n, so n here should be larger than k, and we're going to look at time t, also larger than time s. We're going to assume that here as well, right there. And this is straightforward, right? You apply the definition of a conditional probability, so you get the joint events divided by the probability of the conditioning set. Here's a nice trick here where we're going to start to apply the independence property of the increments. And the way to do this is to first subtract ns from both sides. So I've taken this event here, and I haven't changed it at all, but I've just subtracted in this line here the value of n at time s from both sides. And because that is known, that's equal to k, I'm going to be able to get myself to this third line right here. Once this is in place, I now have two increments. I'm looking at the joint probability of two increments, and those, because the time intervals don't overlap, are independent. And so that gets me to this line right here. And then the rest is just a quick cancellation, right? We get this canceled with this, leaving us with this probability here. So the transition probability really seems to depend on the probability of the increment. In other words, we wanted to kind of count from k to n, starting at time s, leading up to time t. Well, that's the same thing as the increment over that time interval, counting the number of things that we need to count, which is n minus k. Final quick calculation. We'll look at kind of a time reversed scenario, which is fairly interesting. So before, in this slide right here, we were looking at starting in the, given some knowledge of the past, we're going to look at the probability of what happens in the future. Here we're doing the opposite. We are going to be given something, some knowledge about the future. So we know that by time t there are n events. And we're in fact going to say that what probability does this past event have? So maybe a little bit strange, but it's kind of, if you think about it, the reasonable setting for this is that we're not watching the Poisson process, and you missed time s. You didn't see what happened there. You started paying attention at time t, and you saw that there were n events. What is my probability that I had k events? And k has to again be smaller than n, because the Poisson process is increasing. What is the probability that in the past I had k events? And this is going to be similar. It's a little bit more calculation heavy, but again, apply the definition of a conditional probability. That's step one. And the second thing is I'm going to try to kind of reverse time again. So, this is sort of, everything is backwards. I'm going to now try to write it in terms of the probabilities that we're used to, things running forward in time. And so that's pretty simple, just applying the conditional probability where I'm conditioning on the past, I'm able to get to this line right there. And then from here on out, we just use the result on the previous slide. We know what that transition probability from k to n is. And so that's, we computed it on the previous slide, and here there are mostly going to be just a lot of calculations. So I'm skipping the details, but at this point what one would do is plug in all of the Poisson distributions that are involved for all three terms, and then if you do it kind of right, I'm assuming I did it right, pretty sure, you get to this formula, which is sort of curious looking because it reminds one of a binomial distribution with parameters n and s over t, and there's a nice interpretation for it, right? You always want to try to check your answers to see if they have, if they're sensible, and this one is certainly kind of is. So this represents the probability of getting k successes in n IID trials with probability s over t. And if you think about it, you have sort of two regions on the real line, one from 0 to s and one from 0 to t. And now what you're trying to determine is those k events, did they fall in the first interval or the second? And so this is a way of kind of writing this this type of probability. And the ratio of the two times is the success, right? So if s was small, then you have a small probability of getting those k successes, which correspond to the k events in that small time interval. So, kind of the formula matches the intuition, and we'll pause here and go on to the other properties of the Poisson process.